Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In earlier sessions, we have dealt with random variables, continuous, discrete and various generating functions, and also two-dimensional random variables were dealt. Afterwards, we started studying special probability distributions. So, along in line with the special probability distributions, first of all we have taken step to discuss about discrete distribution. A discrete distribution in line with discrete distributions, first of all we have dealt with binomial distribution, and then Poisson distribution concept was introduced, and Poisson distribution's approximation to binomial distribution was also discussed. So, continuing in that, in this session we are going to deal with the Poisson distribution in detail by discussing the mean and variance, MGF of Poisson distribution along with the additive property. Some examples are also worked out to understand the concept of Poisson distribution little further. In continuation with the approximation of binomial distribution to Poisson distribution, let us discuss the Poisson distribution as a limiting case of binomial distribution. So, first of all the Poisson distribution is actually approximated to a binomial distribution, where the binomial distribution has the parameters n and p. N is the number of items and p is the probability of success. So, if x follows binomial distribution with parameters n and p, and if x is a Poisson distribution, it will follow the parameter lambda. Okay. As already discussed in the previous session, as n tends to infinity and p tends to a very small number, then np tends to lambda. Okay. With this concept, from the binomial distribution we can derive Poisson distribution. First of all, when x follows binomial distribution, with parameters n and p, the probability function is written as p of x is equal to x as nc x p power x q power n minus x. The nc x is written as n factorial by n minus x factorial by x factorial into p power x into q power n minus x. So, this NCX, n factorial by n minus x factorial together is written as n into n minus 1 into n minus 2 etc. up to n minus of x minus 1 divided by x factorial into p power x q power n minus x. But what is p? We have taken p as np is equal to lambda. So, p is equal to lambda divided by n and q is equal to 1 minus p. So, what will happen? This will be 1 minus lambda by n. So, p power x. So, in the place of p I am going to put it as lambda by n whole power x into 1 minus lambda by n whole power n minus x. Okay. This n is being distributed for these x factors. N into n minus 1 into n minus 2 etc. up to n minus x minus 1 is the product of x factors. So, what will happen when I distribute it as n by n into n minus 1 by n into n minus 2, this n power x is distributed like this by n etc. n minus x plus 1 divided by n, the whole thing by x factorial and then lambda power x, because the n power x is being distributed here, and you will have 1 minus lambda by n whole power n into 1 minus lambda by n whole power minus x. So, what will happen in the next calculations? You will have lambda power x by x factorial, I will take it outside, and then you will have 1 into 1 minus 1 by n into 1 minus 2 by n etc. 1 minus x minus 1 by n. Okay, that by x factorial is taken outside, and in that the product is 1 minus lambda by n whole power n into 1 minus lambda by n whole power minus x. Now, we have taken the Poisson distribution approximation as n tends to infinity and p tends to a very small number, that is 0. So, as n tends to infinity, what will happen? This 1 minus 1 by n, 1 by n, 2 by n etc. this 1 by n will tend to 0 and 2 by n will tend to 0, x minus 1 by n will tend to 0. So, everywhere it becomes 1. Okay. At the same time, 1 minus lambda by n, this also will become 0 and this is 1 power minus x. So, this will also become 1. So, the remaining is only this lambda power x by x factorial as you take the limit as n tends to infinity. Okay. All these are 1 into 1 minus 0 into 1 minus 0 etc. 1 minus 0 into 1 minus lambda by n whole power n into 1 minus 0 whole power minus x. Okay. So, this becomes lambda power x by x factorial, everywhere it is 1 and this is also 1, and you will have limit n tends to infinity 1 minus lambda by n whole power n. So, what remains? We know that 1 minus lambda by n whole power n as n tends to infinity is e power minus lambda. So, you have only lambda power x by x factorial into e power minus lambda. As limit n tends to infinity 1 minus lambda by n whole power n equals to e power minus lambda. Now, this is nothing but the probability mass function of Poisson distribution. So, what happened? You got the probability mass function of, we started with binomial distributions probability function, and as n tends to infinity and p tends to 0, we arrived at the probability function of Poisson distribution. So, that is why it is called Poisson distribution is a limiting case of binomial distribution. So, we arrived at Poisson distribution probability function as e power minus lambda, lambda power x by x factorial. Okay. This is how Poisson distribution is limited to binomial distribution. Next, we will derive the mean and variance of Poisson distribution as we have been deriving for many problems and many functions. So, mean and variance of Poisson distribution. First of all, let us first find out the mean of Poisson distribution. What is the formula? Expectation of x is equal to, because this is discrete distribution, we have to use summation x into p of x, and p of x is taking the values from x is equal to 0 to infinity. So, summation x is equal to 0 to infinity x into probability function of Poisson distribution is e power minus lambda, lambda power x by x factorial. This x is written in such a way that it is going to get cancelled with x factorial. So, I shall write this x factorial as x into x minus 1 factorial. You can split like this. Okay. And e power minus lambda has got no job inside the summation, because the summation is varying only for x. So, we can take e power minus lambda outside, and you have summation x is equal to 0 to infinity x into lambda power x by, I shall write it in such a way that so that we will be able to cancel x into x minus 1 factorial. Okay. So, x gets cancelled, and you have only lambda power x by x minus 1 factorial. This lambda power x can be written as minus 1 plus 1. Okay. So, this is written as e power minus lambda, lambda power 1 is taken outside, summation x is equal to 0 to infinity lambda power x minus 1 by x minus 1 factorial. So, you have e power minus lambda into lambda, expanding this lambda power 0 by 0 factorial plus lambda power 1 by 1 factorial plus lambda power 2 by 2 factorial plus etc. up to infinity, which is e power minus lambda, lambda by 1 plus lambda by 1 factorial, lambda square by 2 factorial plus etc. up to infinity. This is e power minus lambda into e power lambda. Okay. So, this is lambda alone, this is your mean. Okay. Hence, we have found out the mean. Next, to find out the variance, variance is equal to actually mu 2 is mu 2 dash minus mu 1 dash square, or you can write in terms of expectation as e of x square minus expectation of x the whole square. Expectation of x is what is lambda, okay, where you have to find out expectation of x square. Okay. This is equal to, according to the formula, x square into p of x. Okay. This x square is written in the factorial format as x into x minus 1 plus x into p of x, okay, where you can find out this x square in the factorial format as a into x minus 1 plus b into x, and then find the values of a and b by substitution. X is equal to 0 and then x is equal to 1. When you substitute x is equal to 0 and x is equal to 1, we get a is equal to 1 and b is equal to 1. So, that x square is written as x into x minus 1 plus x. This is what is called factorial format. Continuing with that, you have expectation of x square is equal to summation x is equal to 0 to infinity x into x minus 1 plus x into p of x. P of x is e power minus lambda power x by x factorial. Write this as two summations. Okay. So, this is equal to summation x is equal to 0 to infinity e power minus lambda can be totally taken outside, okay, x into x minus 1 into lambda power x by x factorial plus summation x is equal to 0 to infinity x into lambda power x by x factorial. Okay. I can write this x factorial so that I gets cancelled with x into x minus 1. So, we shall write only the factors which are needed for cancellation and the remaining you put it in factorial itself. So, what happens? This is equal to e power minus lambda, okay, summation x is equal to 0 to infinity x into x minus 1, right. So, x into x minus 1 into lambda power x by x factorial is written as x into x minus 1 into the remaining is x minus 2 factorial. So, that x minus 1 gets cancelled plus summation x is equal to 0 to infinity, you have x into lambda power x by, I shall write it as x into x minus 1 factorial, x gets cancelled, you have only lambda power x by x minus 1 factorial. So, according to the factorial, split the powers of lambda as plus 2 and minus 2 here and lambda power x minus 1 as minus 1 plus 1. So, that it is written as e power minus lambda, this lambda square I will take it outside, lambda square summation x is equal to 0 to infinity lambda power x minus 2 by x minus 2 factorial plus lambda power 1 into summation x is equal to 0 to infinity lambda power x minus 1 by x minus 1 factorial. Okay. When you expand this, this is e power lambda, and this when you expand this, this is e power lambda. So, you have e power minus lambda into lambda square e power lambda plus lambda into e power lambda. Okay. So, this is actually lambda square plus lambda. This is expectation of x square, right. So, to find the variance is expectation of x square minus expectation of x the whole square. Expectation of x square is lambda square plus lambda, and expectation of x we have found out as lambda and it is squared, it is cancelled with lambda square, you have only lambda. So, here for Poisson distribution mean and variance are same and it is equal to lambda. We shall have a break. Welcome after the break. Earlier to the break, we have seen the Poisson distribution as a limiting case of binomial distribution. Also, we have derived mean and variance of Poisson distribution. Next we shall find out the moment generating function of Poisson distribution. We know the moment generating function formula, that is expectation of moment generating function mx of t is equal to expectation of e power tx. Okay. This is equal to summation e power tx into p of x. But what is our p of x here? It is e power minus lambda, lambda power x by x factorial, and the summation will range from x is equal to 0 to infinity e power tx to e power minus lambda, lambda power x by x factorial. Since x is only ranging e power minus lambda is a constant with respect to the summation, we shall take it outside e power minus lambda summation x is equal to 0 to infinity lambda e power t whole power x by x factorial. Okay. So, when you expand the summation, it is lambda e power t whole power 0 by 0 factorial plus lambda e power t whole power 1 by 1 factorial plus lambda e power t whole square by 2 factorial plus etc. up to infinity. This is equal to e power minus lambda 1 plus lambda e power t by 1 factorial plus lambda e power t whole square by 2 factorial plus etc. up to infinity. And this is nothing but expectation, where in the place of x you are having lambda e power t. So, e power minus lambda e power lambda e power t. This is written as e power lambda into e power t minus 1. This is the moment generating function of Poisson distribution. Next we shall arrive at the additive or reproductive property. Because it is called reproductive property, by adding two such variables of Poisson independent random variables, we can produce another random variable. So, that is why it is called reproductive property of Poisson distribution. As discussed in the previous cases, we are going to discuss the additive property using moment generating functions. So, for moment generating function additive property, we must be having the random variables as independent. So, here also if x and y are two independent random variables, then x plus y is also a Poisson random variable. So, first of all we shall take it as x1 and x2. x1 is a Poisson random variable with parameter lambda 1 and x2 is another Poisson random variable with parameter lambda 2. x1 and x2 are independent. Then x1 plus x2 is also a Poisson random variable with parameter lambda 1 plus lambda 2. This only we have to prove. This is the statement of additive property of Poisson distribution. So, how to prove this? Now, x1 is a Poisson random variable with parameter lambda 1. Therefore, its moment generating function is given as mx1 of t. Just now we have proved the moment generating function of Poisson distribution e power lambda 1 into e power t minus 1. And x2 is also a Poisson random variable with parameter lambda 2. So, here you will have mx2 of t into e power lambda 2 into e power t minus 1. So, according to the additive property of a moment generating function, additive property of moment generating function we are going to use, which we have already discussed in the previous sessions. We know that mx1 plus x2 of t is equal to mx1 of t into mx2 of t. So, what is mx1 for Poisson distribution? It is e power lambda 1 into e power t minus 1 and this is e power lambda 2 into e power t minus 1, right. And now we can add e power lambda 1 plus lambda 2 into e power t minus 1. This is actually MGF of another random variable whose parameter is lambda 1 plus lambda 2, and it looks like the moment generating function of Poisson distribution. By uniqueness theorem, any such moment generating function looks like the moment generating function of a particular distribution, then the random variable is said to follow the same this particular distribution. That is, if there are two MGFs which are alike, then the random variables also should have the same distribution. This is what is uniqueness theorem. So, what does it mean? It means that x1 plus x2 is also a Poisson random variable with parameter lambda 1 plus lambda 2, because this is the MGF of a Poisson random variable whose parameter is lambda 1 plus lambda 2. Okay. So, by uniqueness theorem, x1 plus x2 follows Poisson distribution with parameter lambda 1 plus lambda 2. Hence, we have proved the additive property of Poisson distribution. When you discuss the additive property of Poisson distribution, the difference of two Poisson random variables is not a Poisson random variable. That is, if x1 is a Poisson random variable and x2 is a Poisson random variable, then x1 minus x2 is not a Poisson random variable. This we shall see. If x1 is Poisson random variable with parameter lambda 1, x2 is a Poisson random variable with parameter lambda 2, x1, x2 are independent as you can take, okay. Then x1 minus x2 is not Poisson. Okay. We shall see how it is. Take m x1 minus x2 of t. This is written as m x1 of t into m minus x2 of t, because this can be written as x1 plus minus x2. So, this is m x1 of t into m x2 of minus t. This is by the property we have already discussed, m cx of t is equal to mx of ct, where here c is minus 1, right. So, what will happen? M x1 of t is the moment generating function of Poisson random variable, and it is written as e power lambda 1 into e power t minus 1, and m x2 of minus t is e power lambda 2. In the place of t you are having minus t. So, e power minus t minus 1, and these two cannot be combined, and you can't write lambda 1 minus lambda 2. This is not in the format of e power lambda 1 minus lambda 2 into e power t minus 1, you can't write. And so that this is not the MGF of the random variable x1 minus x2, and since it is not the MGF, the random variable x1 minus x2 is not a Poisson random variable. Therefore, difference of two Poisson random variable is not a Poisson distribution with parameter, as you say, lambda 1 minus lambda 2. Okay, it is not a Poisson distribution. Next, we shall deal with one example. The number of monthly breakdowns of a computer is a Poisson random variable with mean equal to 1.8. What does we have shown? The mean is represented as lambda, right. The parameter is also lambda. So, when a problem is given, even if it is not mentioned that it is Poisson random variable, when in a problem when you are given only the mean value, because mean is representing the only parameter lambda, you can do the problem with Poisson distribution, okay, because only mean is given, then you can proceed with the mean as lambda and find out the respective probability. Okay. Find the probability that this computer will function for a month without a breakdown, with only one breakdown, and with at least one breakdown. We shall start the solution. The mean is given to be equal to lambda, and lambda is equal to 1.8. X is the number of breakdowns. What is the first question? The first question is, you find the probability that the computer will function without a breakdown. Without a breakdown means there is no breakdown at all. So, P of x is equal to 0. Before that, you must write what is P of x is equal to x. Because it is a Poisson random variable, we shall have e power minus lambda, lambda power x by x factorial. Even you can substitute this lambda and keep it constant e power minus 1.8, 1.8 whole power x by x factorial. So, p of x is equal to 0 means e power minus 1.8, 1.8 whole power 0 by 0 factorial, which is equal to e power minus 1.8, and the value is equal to 0.1653. The second question is, find the probability that the computer will function with only one breakdown. With only one breakdown means p of x is equal to 1. P of x is equal to 1 is e power minus 1.8, 1.8 whole power 1 by 1 factorial, and what is this value is equal to 0.2975. Okay. What is the third question? What is the probability that it functions with at least one breakdown, and at least is mathematically represented as greater than or equal to 1. Greater than or equal to 1 means it starts with p of x is equal to 1 plus etc. it goes on up to infinity, because x takes the values from 1 to infinity. So, this can be written as 1 minus p of what is left out, x is equal to 0, and x is equal to 0 we have found out in the previous slide as 0.1653, okay, 0.1653, and what is this value equals to 0.8347, okay, and this is the answer. Hence, we have arrived at the solution of this problem. So, in this session we have dealt with the Poisson distribution in detail, as Poisson distribution as a limiting case of binomial distribution, and then mean and variance of Poisson distribution, moment generating function of Poisson distribution along with additive property. Also, we have proved that difference of two Poisson random variables is not a Poisson random variable. Also, one example has been worked out to understand the concept of Poisson distribution little further. So, based on the example worked out, this exercise can be done. A car hire firm has 2 cars which it hires out day by day. The number of demands for a car on each day follows Poisson distribution with mean 1.5. So, in this problem only the mean value is given. Mean represents lambda, that is a parameter required to do a problem in Poisson distribution. Calculate the proportion of days on which neither car is used. Neither car is used means the demand is 0, right, and some demand is refused. There are only 2 cars. When the demand will be refused? When the demand is more than 2 cars. If it is 2 cars, we can give the 2 cars on hire, but if the demand is more than 2 cars, then definitely we have to refuse the demand. So, this particular second problem we have to deal with deal it as p of x greater than 2. Thank you.